This is lesson 6 called Sum of Products Design. In this lesson we'll see how to design a circuit involving ands, ors, and NOT gates given a particular truth table. Let's look at this exclusive OR truth table. You remember that the output of an exclusive OR gate is 1 if either input is 1 and the other is 0. Now let's try to design a circuit that will produce a exclusive OR gate using just ands, ors, and NOT gates. To do that, we're going to define what we call a minterm. Now a minterm is something that is 1 for a particular combination of inputs, and it involves the product of the terms, such as NOT x and NOT y in this case. Now notice that if the x is 0, we must NOT it to make it a 1, because an AND gate, everything must be 1, because if you AND anything with a 0, you get 0. So to make minterm M01, if the input is 0, we'd have to NOT it to get a 1 here. If the input y is 0, we need to NOT it to get a 1 here, and 1 and 1 is 1, so the minterm would then be 1. How can we make minterm M1 1? Well, if x is 0, we must NOT it to get a 1. If x is 1, it's already 1, so we just leave it, and again 1 and 1 is 1. How do we make M2 1 if x is 1 and y is 0? Well, x is already 1, so we just leave it. X is 0, so we need to NOT it, so 1 and NOT y would be 1 if x is 1 and y is 0. Of course, if they're both 1 coming in, then we can just say x and y, because 1 and 1 will be 1. So these are the definitions of minterms. Remember, minterms are 1 for a particular combination of inputs. Now they're very easy to remember. We can just do it by inspection. If you have a 0 here, you NOT it. If you have a 1, you don't NOT it, and you AND them all together. So M0 is just NOT x and NOT y. M1 is just NOT x and y. M2 is just x and NOT y. And M3 is just x and y. So they're very easy to remember. Let's see how we can use those to design our exclusive OR gate. What you do is you look at the output that you want, z, and you look for the 1s in here. We want z will be a 1 if either this term is 1 or this term is 1. But remember, minterms are 1 for a particular input. So z is just this minterm M1 or this minterm M2. You see why we call it a sum of products. We just put in the definitions of M1 and M2 now. Z will be NOT x and y, that's this term, or x and NOT y. That's all there is to it. We can write basically by inspection here what the z is in terms of x and y in terms of a sum, that is an OR, of products, that is AND gates. Now, we can now draw the logic circuit for this. Here is the output we want. We need some NOTs, so we'll use this convention. We'll make our inputs come in from the top, x and y, and then you can think of these lines as being wires, so this wire here is just x anywhere along this wire. We'll put an inverter here, so this is NOT x along this wire. Y, we'll just bring a wire down here for y, and another inverter makes this NOT y. Well, now we need two AND gates, one for this term, one for this term. So we put two AND gates here. And to get NOT x and y, well, we just wire it up. Connect this to NOT x. Here's NOT x. Connect this one to y. So this output is NOT x and y. To get x and NOT y, just connect this input to x. There's the wire for x. Connect this input to NOT y. There's the wire for NOT y. This output is x and NOT y. And finally, to get z, we just OR them together with this OR gate. So we've now made a circuit whose output z will produce the exclusive OR of x and y. Now, when you write a logic equation like this involving parentheses, we can actually remove the parentheses if we remember this precedence of the logical operators. First, all the NOTs are done first. So in here, not x and not y are done first. Then all the and operations are done next. So we produce x and not y, and then x and not x and y here, and x and not y here. And finally, the OR operations are done last. So if you write this logic equation without the parentheses, you get exactly the same effect as if you included the parentheses. Okay, in the next lesson, we'll look at how to produce the same exclusive OR gate using what's called a product of sums design.